This one is 2015, June, paper 1-2 lah. Two light waves of the same frequency are represented by the diagram. What could be the phase difference between the two waves? What's your answer? It's about phase difference. Ken?
Wait. Teacher, which page is this?
Which page? 172. One 173 there lah, about there. Ken? Yep. What is your answer? What's your answer? What's the phase difference? Important you do the worksheet. Right? You won't have time to do past paper, at least you do the worksheet to reinforce what I've teach you. If not, you are wasting your time and money. You want to do well in physics, you have to solve problem, no shortcut. Because A level is not memory work. It's more of application, your basic principle. And look at the corresponding point. This is the wave. Right? This is the wave going up. This is the wave going up. So from these two, the difference is about 100, 200, more than 250. So 260. See, if you take the crust, there's the crust, that's the crust, it's about 100, it's about 200, so the difference is 100. If you use that,
Oh, okay.
I doesn't tell you which one to use, you can use anyone. Right? You can either take this angle theta or take this angle, same thing. See which is given. Can.
Okay.
Let's try another one. How about this one?
Looks like A.
Okay, you're right. This is 90. This one to here 90. This difference is half of 90 is 45. Okay, good. Okay, or can use the formula to calculate. Can do mentally if you can. Okay, let's try one more. One more after this. Graph represent two sound wave X and Y. Which row shows the intensity and frequency ratio for X and Y? Can? It's a partial question. Can or not? Can or not? Just use the intensity formula. I is Ka square. So X is 4 millimeter. Don't need to change the unit because we are taking ratio. Okay. Ka, K4 square, K2 square. The answer is 4. And frequency, Fx, Fy. Right? Frequency equals 1 over period. We can read the period. Period for X. X is about 1.8 there. It's about 1 over 1.8. Don't have to worry about the unit because you are taking ratio. And frequency of Y is a broken line. That is about 3.6 there. 3.7, 3.6 there. So 1 over 3.6 times 3.6 denominator and 3.6 numerator, you get 2. Answer donkey. Can?
Okay.
Okay, one last one. Number 14.
Teacher, can I join my computer? My computer is working now.
Say again.
Can I join with my computer? My computer work
Can.
already.
No problem. Do whatever is convenient for you. No problem with me.
Okay.
What's the answer? Is 2002 November, number 27. Basically, you have to use intensity is proportional to amplitude square. And then whatever is given you, amplitude A, intensity is 3, write down. And what is the intensity of the wave of the same frequency that has amplitude 2A? Right? Work it out again. The intensity is equal to K, right? This is 2A square. So it's 4 Ka square. Ka square is 3. So it's 12. 10.
Um.
Anything not clear?
Yeah. Okay.
Make sure worksheet do. If not, you are wasting your effort. You forget everything.
Yeah.
Okay, let's start. today's topic. Okay, let us go to page 167. We have finished progressive wave, how to represent the wave, and we have learned different terms, wavelength, period, phase, and phase difference. So hopefully we can cover, this is pictorial form lah, what we are going to cover lah. Right, this is from your syllabus, transverse and longitudinal wave, we are going to cover today, 7.2. Determination of speed, frequency, and wavelength. Then after that, Doppler effect, electromagnetic spectrum, polarization. Right? Hopefully we can cover all of them. Right? Progressive wave, as we say, summarize yourself. Right? Review yourself, summarize yourself. In progressive wave or traveling wave, energy is transferred from one place to another by vibration. Right? The blue one is the one going and reflected, the red one is the reflected wave, so its energy is transferred. Then you need to know how to read the wavelength, what's the crust, what's the trough, how to read the period, what's the amplitude, and then how is period related to frequency, and then phase, different time and distance, must know these two formula. Then intensity equals to power over cross-sectional area. Intensity is, this one is amplitude, this cross-sectional area, normal to the intensity. Then we cover cathode oscilloscope to measure frequency amplitude of the wave. Okay, page 167. That's your syllabus. Okay, we got types of waves, longitudinal waves, transverse wave. Longitudinal wave, this is your hand, right? It's vibrating to and fro. That's your source, right? Left to right, left to right. And then the wave flow into the spring. This longitudinal wave. And transverse wave is the hand is moving up and down. Right? The hand hit the source up and down. And then the wave move along to the other end. Right? Remember, it transfer energy. Okay, let's go to transverse wave. What is it? What is transverse wave? The displacement is perpendicular to the direction of propagation. Propagation is travel of the wave. Example, electromagnetic wave, light wave, radio wave, microwave, ripple or water waves. We can think of it as this the instant photograph of the wave moving. Right? Know how to represent it. This direction of travel and direction of displacement or vibration. Right? Don't worry about the equation. This one, if you are going to study physics in first year, you will learn equation. The wave can represent by equation. Right? That's your ripple tank. There's your spherical Doppler. Dipper. You want spherical waves. There's your plane dipper. You want plane waves. Okay, the function of the parts. The experiment has to be carried out in a dark room. Right? There's a vibrator. Connect to a power generator. The power generator is not shown. The power generator is basically the one that allows you to change the frequency of the vibrator. Causes the dipper to vibrate, right? Up and down on the water. For plane waves, a plane dipper is used. And for circular wave, a spherical dipper is used. Power generator controls the frequency of the dipper and thus the waves. The lamp projects, that's the lamp, right? It's done in a dark room, that's why you need a lamp. So the wave is formed on the water surface here, and then the lamp will project the shadow onto the screen. Screen is just a piece of white paper. Lah. Shadow of wave is projected on the screen placed on the ground. Right? It just came out 2013 November, paper 23. Right? Where they ask you, a wave in B was produced in ripple tank. Describe briefly with the aid of a sketch diagram how the wave may be observed. Just give a two-dimensional drawing, that's not good enough. Right? Label your diagram, that's your water, that's your ripple tank, that's your stroboscope, that's your lamp, that's your elastic band, that's your vibrator, that's your support, there's a screen on the ground. Right? Describe briefly, explain carry out in dark room. What's the purpose of stroboscope? Adjust stroboscope adjusted to frequency of wave. The wave is frozen. That means where the frequency of the wave and the frequency of stroboscope is the same, then the wave look as if it's not moving. Right? These are various forms. Right? Don't need to draw so sophisticated. This one you did in your O-level or SPF, where the school cannot afford to buy stroboscope. Stroboscope is quite expensive. It's just like a light that goes off and on. So you use the slot. This one is cheaper. So if you turn the stroboscope here at the right frequency as a wave here, then the wave as if it's not moving. Okay, this is your spherical wave or circular wave. That's the ray, show direction of travel of the wave. And then that is your wavefront. Between wavefront and wavefront is your wavelength. How do we get the dark, the wavefront? Okay, the light coming in, this one normal to the surface will go straight through. This one at an angle to the surface, right? It will not go straight through. It's reflected towards the normal. That's the surface. The normal is about here. So that's direct through. So it's reflected towards the normal. Like a lens. You don't need to know that detail. But I just go into detail to help you understand. So that's what is happening. This one will be bright. This one, little light goes through, will be dark. So you see bright and dark lines. Okay. Wavefront, ray, spherical wavefront. Wavefront are lines or planes that join points vibrating in phase. Usually we will consider as joining all the crust together. They are in phase. Rays are perpendicular to the wavefront, showing the direction of travel of the wave. So the rays show us the spherical wave is moving out in all directions. Right? Spherical wave is if it's 3 dimension, circular wave is 2 dimension. Right? Usually we don't like to draw wave because it's very difficult to draw wave. Like this one, you can see it's not evenly drawn. Okay, so we prefer to draw wavefront. These are pictures you can get from internet. So we draw wavefront good enough. The wavefront represent you join the crust of the wave. The wave can be that way. And the ray show the travel, direction of travel. Stop me if you are going to ask question. Right? If representing the grass, there's a two wavefront. Measuring frequency, wavelength, and speed of wave. Right? Depend on how you count, but usually we count wavefront. This is the first one. This is the 11th wavefront. For ripple tank experiment, turn the stroboscope at the lowest possible frequency, which will freeze the wavefront. Freeze means it doesn't move lah, as if it's stationary lah. So frequency of wave equals frequency of stroboscope. So how to find the wavelength? Use a ruler to measure x. Distance between the first and the 11th. Then divide. 10 wavelength. Right? Remember, 10 wavelength, we didn't count this one 0, we count the first. That's why 11 become 10 wavelength. And speed is just your v equals to f times lambda. Okay. Frequency of stroboscope you can read from the instrument. Sound waves. Sound waves are longitudinal waves. Sonic are sound waves that we can hear. Audio frequency is about 20 hertz to 20 kilohertz. Ultrasound are high frequency sound waves beyond the range of human ear. So it's usually more than 18 kilohertz. You study under application. Speed of sound usually will be given you, but you should know roughly in case they ask you for objective question. What's the magnitude of speed of sound? It's about 300 there. Sound waves are mechanical waves. Needs a medium to travel. Sound waves travel through gas, but not through vacuum. Sound waves travel through air as a series of compression and reflection. This is just for your info. Frequency of light is much larger than frequency of sound wave. Frequency there of light greater than that of sound wave. Wavelength of sound is larger than wavelength of light. That's the estimated wavelength corresponding to this frequency. That's the wavelength of light, very, very small. You need to memorize the magnitude involved. Longitudinal wave. Must remember, the displacement or vibration is parallel to direction of travel propagation. Example, sound wave. As sound wave pass in air, is alternately compression and reflection. You can see the diagram here. The tuning fork is the one that produces sound. So where the air particles are together, compression. Where the particles are far apart, these are reflection. Or we can use slinky spring. Right? Must know how to represent it. Direction of travel, horizontally. Direction of vibration, the same, horizontally. Right? This is a displacement. Okay. Variation of pressure and displacement with distance. That's your air particle. That's your compression. That's your reflection. Right? And the compression is here, where the displacement is 0. And the reflection also displacement is 0. But how do we see the difference? Right? We'll go into more detail in a while. To a compression, all the particles are moving towards the compression. Whereas if you look at the reflection, they are moving away. They're moving away from reflection. From compression to another compression is a wavelength. Right? Compression to another compression is one wavelength. For compression to a rarefaction is half a wavelength. Compression to rarefaction, half a wavelength. Displacement to the right is positive. Right? That is conventional. Displacement to the right is positive, but to the left is negative. Right? We look into more detail this one. You find that that's the variation of pressure. Compression are region of high particle density or high pressure. Particles near a compression are displaced towards it. That's what we have said. They are always towards the compression. Rarefaction are region of low particle density or low pressure, okay? Lower than atmospheric pressure. Particles near rarefaction are displaced away from it. Here, there's a rarefaction that are displaced away from it. And you should be able to read from these two diagrams. That's where it starts, that's where it starts. Right? The pressure and displacement graph are 90 degrees out of phase. Okay, where there's no sound, we can imagine that the layers of air, these are layers of air, are evenly spaced. And if we look at a compression, this is a compression, it's not moving, that layer not moving. The one to the left is moving to the right. The one to the right is moving to the left. So that's why we increase the density. Right? We look at rarefaction. That's a rarefaction. It's not moving. That's the original position. So it's moving away from the rarefaction, the layer of air. Right? So we can see from here. Right? That's the point. So it's moving positive. Positive is to the right. Positive is to the right. Same as here. This one is here. Right? It's moving negative. Negative to the left. From here to the left. So that's your compression. Rarefaction, the same thing. That's your rarefaction. Right? That's your rest position. It's moving to positive. Positive means to the right. Same here. That one is here. Right? It's negative. So it's moving to the left. Okay. Any comment?
No.
Okay. It's just another diagram to show you the pressure changes. That dotted line is the atmospheric pressure. So it's either there's a decrease in pressure or there's an increase in pressure. So at a compression, there's an increase in pressure. Particles, there are more particles there. Rarefaction, there's a decrease in pressure. Less particles there. Okay, we got 10 minutes left in case we got cut off. Determine the frequency and wavelength of sound, just for info. Then you can use a loudspeaker. Power generator is the one that produces the frequency. Audio, or we call it audio frequency oscillator. A loudspeaker produces sound wave of constant frequency. Outline how a cathode ray oscilloscope may be used to determine this frequency. This one came out in 2010 November, paper 23. Just a simple diagram, good enough. Connect microphone to the Y plate of the CRO. Adjust the CRO to produce a steady wave of 1 cycle or 2 cycle on the screen. Measure the wavelength. Wavelength is the period of the cycle, and note the time base. So calculate the time. The period is your wavelength times your time base, and frequency is 1 over the period. Right? production of sound wave. Okay, there's a power generator, audio frequency generator. Audio frequency oscillator produce a sinusoidal varying voltage in the audible frequency range. That's why we call it audible or audio frequency. Loudspeaker converts the varying voltage to sound waves. Sorry, something wrong with the computer. Doesn't like me doing something legal. Sorry about that. Just press something illegal.
Huh? What did you do?
I press I press internet picture lah. Yeah.
Oh,
Sorry. What is happening? Why is not obeying my command? It's not obeying my command. What is wrong? Okay, finally got it. Don't worry about that. Okay, let's try some worksheet. We have more or less completed. Let's try some worksheet question. Okay, what is the answer for this one? Transverse wave. Yeah. For transverse wave, what is the wave? What is the wavefront? What is the wavefront?
I think it's the
It's our partial question.
A.
A. A phone rings and lights up. Which type of wave are associated with the phone's operation? What's the answer?
C.
Okay, answer C. Just in case it got cut off, I just show you a video.
Okay.
What is happening?
There's no audio.
Can? Any problem?
No audio. I think you can send it into my WhatsApp and watch the video.
As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away,